Hey everyone, welcome back to Cam Room 5. So as we head towards our exam, we're going to start rate of reactions today. This has been one of the chapters that has been requested a lot of times by kids, so let's start doing this. What is rate? The word rate can also be used instead of speed or velocity, so these words are interchangeable over here. Rate, speed or velocity of a reaction. So it is the change in the amount of reactants or products. Definitely reactants are being decreased, products are increasing. So it is the change in the amount of reactants or the products per unit time, per every second or every minute or every hour. The amount could be taken in the units of moles or the centimeter cube of a gas, let's say, the change in concentration or the change in mass. These are all indicators of the amount, while time could be seconds, it could be minutes, or it could be hours. So we are talking about these changes per unit time. Yeah, exclamation marks better. So when we talk about any particular reaction, like let's suppose we're talking about the reaction between hydrogen gas and fluorine gas to produce gaseous hydrogen fluoride. It's a reaction which produces HF. In the beginning of the reaction, there's only hydrogen molecules and fluorine molecules which are constantly colliding with each other and among themselves. But as time proceeds, a lot of molecules would make the product, which is HF. You can see in the beginning, in the start, there's only H molecules, the two red dots together, and there are two F dots together, which are F molecules, F2 molecules I should say. So the particles are colliding with each other, and there's a certain frequency of their collision, which means how many times they're colliding. But as the reaction proceeds, they start making HF. A lot of molecules are still H2 and F2. I'm not saying all the reactants have made the product, but a lot of them have started making the product. And some of them you can see are still F2, and some are still H2. As the reaction proceeds further, you can see all of the reactants would have made their product, so there won't be any H2 or any F2, there would be only HF molecules. You can see all the particles have changed their appearance. Now they are not two red dots or two green dots, they are red dot with a green dot, so HF, hydrogen fluoride gaseous molecules in the end. These molecules are obviously colliding with each other and with the container because they are gases. This is a property of a gas. Now when we talk about a graphical analysis of the rate of reaction, we take time on the x-axis and we take the concentration, let's suppose, or volume or mass or amount or anything on the y-axis. You can see in the beginning there were only H2 molecules and F2 molecules. So in the beginning, the concentration of H2 and F2 was really high, which decreases with time. It may become zero, it does not become zero, it depends on the completion of the reaction. But at the end of the day, it becomes constant, while the concentration of HF increases. HF is a product, hydrogen fluoride is a product, its concentration will gradually increase and then it will become constant after reaching a maximum value. While the concentration of hydrogen and fluorine will decrease with time. It decreases with time because they are reacting. Let me write it over here. H2 and F2, yeah, their concentration decreases with time and then it becomes a constant. You can see the gradient of the graph was really high in the beginning, but then the gradient decreases and then the gradient even further decreases. In the beginning, the gradient of the graph is really high because the rate of reaction was really high in the beginning. So you should know that in a graph, the gradient of the concentration over time always tells us about the rate of reaction. Since the gradient is decreasing, which means the rate is decreasing. Why is the rate decreasing? Because the concentration of the colliding reactant particle decreases. You can also see in the product graph as well that the gradient was really high and then it decreased. Let's talk about the overall rate of reaction analysis, that what should we know and why do we know this and what's the explanation behind it. The first thing is that in the beginning, when we talk about a reaction, obviously there's the point when the reaction just started. So in the beginning, the rate of reaction is highest, or you can say the reaction is fastest. Now, why is it fastest in the beginning? It is fastest in the beginning because the concentration of the reactants is really high. Since the concentration of the reactants is really high, which means more particles of reactants per unit volume. Since the concentration is really high, the particles are really crowded, their collision frequency is really high. What's collision frequency? It means number of collisions between the reactants per unit second or per unit time. So it is the number of collisions per unit time. Per second or per unit minute or per unit hour, whatever unit of time you're using, that depends on it. The second point we should know is, as time proceeds, as time moves further, my writing is really becoming worse. So as time passes, the rate becomes slower, or you can say the rate of reaction decreases with time. Why? Because reactant particles are used up. And as the reactant particles are used up, the reactant concentration decreases. Since the reactant concentration decreases, they are used up, or you can say, there are less particles per unit volume. So less particles per unit volume result in less collision frequency, less collisions per unit second, which means obviously the rate would become slower. After a certain time, you can say after a very specific time, the rate becomes zero, the reaction stops. Definitely, it does not mean that the reaction is completed over here. Maybe there was some contamination that did not result in 100% product, but at least the reaction stops. There's no further change after a while. Because all the reactants used up, the reactant concentration becomes zero. Because they're used up obviously in making the product. So the collision frequency becomes zero. There is no collision per unit time. Now, we know that we have studied in the last few videos about how do we measure the rate of reaction. There was one method of rate of reaction measurement that we discussed in one of the previous videos. It was designing an experiment for the rate of reaction. So designing an experiment to measure the rate of reaction. Remember, we talked about a reaction between aqueous hydrochloric acid, obviously acids are aqueous, with solid calcium carbonate to produce calcium chloride, water, and carbon dioxide gas. And carbon dioxide was gas. We know hydrochloric acid is obviously aqueous, calcium chloride is solid, salt is aqueous, and water is liquid. We took a conical flask with the contents on a mass balance. We had a piece of cotton swab on top of it. We had a test tube filled with hydrochloric acid, which had a thread around it, and then was calcium carbonate at the bottom of the flask. We talked about a person stretching the thread so that the test tube falls and the hydrochloric acid reacts with the calcium carbonate. As soon as the person pulls the thread, the hydrochloric acid starts reacting, the gas was produced, and the gas escapes from the system, so the mass of the system decreases. It is all because calcium carbonate was reacting, carbon dioxide was a gaseous product which was escaping. You measured the time, and every 30 seconds or every 1 minute, you were measuring the change in the mass from the electronic mass balance. And you were recording that in 1 minute the mass decreased to this value, in the second minute the mass decreased to this value, and so on. So you would be able to notice that the mass decreases with time. In the first minute the mass decreases really quickly, in the second minute it again decreases, and then it goes on. The initial mass was really high, but as carbon dioxide escapes, the mass decreases. The mass does not become a zero in the end, and that is because there are some other contents still in the conical flask, like calcium carbonate, like water, like the piece of cotton swab, like the aqueous calcium chloride, and whatever the other contents are still there. The unreacted calcium carbonate could be there, so these were still present, and that's why the mass wasn't becoming zero. You can see the gradient is really sharp, is really high in the beginning, then the gradient decreases, and then finally the gradient becomes zero when the reaction stops. So a zero gradient indicates a completed reaction. In today's video, let's also talk about the second method of measurement of rate of reaction, which is method number 2, which is the gas volume measurement respective of time. So gas volume collection with time measurement with respect to time, because obviously rate is obviously a function of time. We're going to have a similar reaction between, let's say, calcium carbonate, hydrochloric acid, and then we get the similar products. We're going to get calcium chloride, we're going to get water as one of the products, and we're going to get carbon dioxide as one of the products. Okie dokes. So we have a similar conical flask like last time. We have a gas syringe. This time we don't have cotton, but we have a rubber bung. We want to stop the gas from escaping. So rubber bung is going to help preventing the escape of gas. You can use a piece of cork or a rubber bung. We have calcium carbonate, and then we can add hydrochloric acid over here. As soon as we add the hydrochloric acid, for example, as soon as we add hydrochloric acid over here, the hydrochloric acid reacts to produce the carbon dioxide gas and the other products. So you will see the bubbles of colorless gas, which is carbon dioxide, and your gas syringe will expand to collect it. You can measure the volume of the carbon dioxide gas every 30 seconds or every 1 minute, or depending on your experiment. You can notice the volume of the carbon dioxide gas is escaping. If you draw a graph, you would be able to notice that as the time proceeds, the volume of carbon dioxide gas increases. Why does it increase? It increases because carbon dioxide is constantly collected in the gas syringe. You can use the graph, and you can also see that as the time proceeds, the gradient decreases. The volume is still being collected, the volume is increasing, but the gradient of the graph is decreasing, which indicates that the reaction is becoming slower as the time proceeds, and finally it stops. So in the coming video, we'll talk more about how the rate of reaction proceeds. Thank you guys.